Hello students, and welcome to our continuing lesson on vectors. And in this particular video, we're going to talk about how to find an angle between two vectors, and then we'll apply it to some specific problems. So here I have two vectors. V is -4, 3, and U is 6, 7. And I want to find the angle between the two of them. So let me just sketch this out. So V is -4, 3, so it's approximately there. And then U is 6, 7, so it's going to go over 6, go up 7, so it's quite a bit over here. And then I am looking for this angle right here in between the two of them. And there are several ways that we can approach this problem. And we will derive a general formula later on. For the time being, though, we are just going to work at this problem using triangles. So I know that if I extend this out, this is going to be 6, this is going to be 7. And I know that on the other side, if I extend this length, this is going to be 4, and this here is going to be 3. Okay. My drawing isn't perfectly to scale, but I think it works. And we have some angles here that we can use. I know that this angle in the red triangle here, we'll call this theta 1. And we'll call this other angle over here theta 2. So I have theta, theta 1, and theta 2. Okay. And you can see here that if you want to find theta, you just use the fact that these three angles add up to 180 degrees. So this is the equation that we're going to use here. Theta is equal to theta 1 plus, I'm sorry, let me rewrite that in a better way. Theta plus theta 1 plus theta 2 equals 180 degrees. And if we want to, and again, we're solving for theta. That's the unknown. Okay, this is the unknown angle right here. So if we want to find that angle, we can just figure out what's theta 1, what's theta 2, put that into this equation, and then solve. Okay? And it's not terribly difficult to find theta 1 and theta 2. If you want to find theta 1, just use the inverse tangent. So I know that the tangent of theta 1 is equal to 7 over 6. That's opposite over adjacent. That means the inverse tangent of 7, 6 is equal to theta 1. And then for theta 2, I know that the tangent of theta 2 is equal to 3 over 4, and that means the inverse tangent of 3/4 is equal to theta 2. And I'm not gonna punch this into a calculator just yet because it can kind of cluttered, and I don't want to get too much rounding going on, because I might end up with a wrong rounded answer. So now I can actually solve this equation. I know that theta is equal to 180 minus theta 1 minus theta 2. Then just substitute that in. Theta is equal to 180 minus the inverse tangent, because I know that theta 1 right here is this value, the inverse tangent of 7, 6, minus theta 2, this right here, well, that's just the inverse tangent of 3/4. And now you take out a calculator and you type all this in, and you get that theta is approximately equal to 93.73 degrees. And so there you have it, a problem that asks you to find the angle between two vectors. And we solve this entirely by using our knowledge of triangles. Now let's try a sort of a similar problem, but with a slight difference. So here I have a problem where the first vector is 6, 2, and the second vector is 1, 8. So 6, 2, we're going to go pretty far over 6, up 2, so it's approximately here. And then the second vector is 1, 8, so we're going to go 1 over and up 8. So pretty far up here. And then we are looking for this angle. And just to be perfectly clear so that we're not cluttering, we're not mixing things up, this length here was 6, this here was 2. And we have some overlap here. This length here was 1, and again, I'm not drawing everything perfectly to scale, and this green line here is 8. And we want to find the angle between the two blue lines. Okay. Well, this isn't terribly difficult to do again either. So it's just we got to be careful because the picture can get cluttered awfully fast. Okay. So we are looking for theta, and we essentially have 3 angles that we are working with here. Theta 1 is this red angle right here. So I'm going to call this theta 1. Theta is just the blue angle there. And then we have one more angle. We're going to call this theta 3, this green angle right there. Okay. That's theta 3. And this becomes somewhat of a geometry problem. And we use our equation here. You can see that the red angle plus the blue angle is going to be equal to the green angle. So the green angle is both the blue and the red. And this is just the angle addition postulate. So we can see here that theta plus theta 1 is equal to theta, I should call this theta 2. I'm sorry, I don't know why I call this 3. This should be a 2, theta 2. Okay. Theta, the blue angle, plus theta 1, the red angle, is equal to theta 2, the green angle. Okay. And again, we're solving for theta. Keep in mind that's our unknown. So theta is going to be equal to theta 2 minus theta 1. And now we just use some trig to find out the values of theta 1 and theta 2. Well, theta 1 is part of this red right triangle here, and so you can see that tangent of theta 1 is equal to 2 over 6, or 1/3. Therefore, theta 1 is equal to the inverse tangent of 1/3. And whatever that number is, we'll figure it out later when we substitute it into here. For the green angle, you have you have tangent of theta 2 is equal to 8 over 1. That means theta 2 is equal to the inverse tangent of 8 over 1, or 8. Okay. And now we can just take these two values here for theta 1 and for theta 2 and theta 1 and then substitute it in here. So now I know that theta is equal to the inverse tangent of 8 minus the inverse tangent of 1/3. And if you type that into a calculator, you should get that your angle is approximately equal to 64.44 degrees. And there you have it. We've done 2 examples here of how to find the angle between 2 different vectors. Now, I'm going to hit pause, and we're going to transition to a problem where we actually use this fact to solve an actual practical application. So here we have a problem that says a 250-pound force in the direction of 3,7 moves an object from 0, 0 to 5, 8. How much work is done by the force? Okay, so let's just sketch this out here. I have a 250-pound force in the direction of 3, 7, so it's going 3 over 7 up. Okay, but keep in mind this is not the same vector as this one. Okay, the vector of the force and 3, 7, that gives us they're in the same direction. So you have this vector here. Let me use a different color to make this crystal clear. You have this vector here. Okay. We'll call this f. That's the magnitude of f. Okay. And the magnitude of f is 250, which is different than the magnitude of 7.3. It might go, you know, exactly 7.3 or 3.7, sorry, or it might go a little bit more, or it might go a lot more. But this 3.7 here only gives us the direction. It does not tell us the exact components of this force. Okay, and then it moves an object from 0, 0 to 5, 8. So it goes from 0, 0, so approximately 5 over and then 8 up. 5 over and 8 up. So I'm going to call this other vector here vector m. I don't know if that's standard usage of letters here, but we'll call that vector m. So in other words, what's happening here is the force is pulling an object, but the object moves in this direction, and we want to know how much work is done by the force. Now, you have to be careful here that it's not as simple as just finding, as taking force times m, okay? Because, I'm sorry, I don't want to call this m, I want to call this d. Sorry. D. It's the distance that the force is moving, okay? That the object is moving. Now, we have to be very careful here because it isn't so simple as figuring out, as just taking these two and multiplying it together, because only some of this force is actually effective. So what we need to do is do a little bit of work here, and we need to figure out how much of F, so we're trying to figure out how much of F actually moves the object. Okay. In the direction of D. In other words, that's the effective force that we've talked about in the previous video. Effective force. Okay. So what we are looking for here is this vector here. So we form a right triangle between the effective force and the direction of movement. And we are looking for this purple vector right there. Okay, that's the effective force. And this is getting a little bit cluttered here, so I'm going to say that this right here is E. Okay. That's the effective force, the component of F that is actually contributing to the motion of the object. So the work that's done is the magnitude of E times D, the magnitude of D. Okay. And so what remains for us to find is the magnitude of E. Well, let's do a few things here. Let's figure out the magnitude of D. So we know that this is 5, this is 8. Okay. So then D is going to be square root of 5 squared plus 8 squared, which is equal to 25 plus 64. So that's going to be the square root of 89. So whatever it is that E is going to be equal to, we multiply that by the square root of 89, and we'll get our answer. But E is a little bit difficult to figure out, but we can still do this. This angle right here is going to be very helpful to us in order to find this side. So if I draw the theta in here between the purple vector and the red vector, we can see that cosine of theta is equal to E over F. So then F cosine of theta is going to be equal to E. So now we need to solve for theta. Okay. And if you rewind the video a little bit, you can see now this is a very similar problem to two of the previous problems that we've seen before. If we could find theta, we could substitute it into here and use it to help us find E, okay? Because we already know that F is 250. So I'm gonna redraw this problem a little bit, just so that it's not so cluttered for us anymore. So I know that you have this triangle here, 3, 7, and there's an angle theta in here. Well, we're gonna wait. Let me draw this a little bit bigger. Sorry. So you have this angle right here. And I'm going to call this theta 1. This is 3. This is 7. You have another angle that extends out here. And it extends way up here. And this triangle here has the green one has a length of 5 and a height of 8. And we're going to call the green one here theta 2. And then the purple one is this little sliver right here, which is the same angle that we're looking up here. Let me move my picture up, sorry about that. So this is the purple angle here is theta. Okay. And we can see here that similar to the other problems, theta is going to be equal to theta 1, because theta 1 is the entire blue angle. It's going to be equal to theta 1 minus theta 2. So to solve this problem, we're going to solve it similar to what we did before. I know that theta 1 is going to be equal to the inverse tangent of 7 over 3. And I know that theta 2 is going to be equal to the inverse tangent of 8 over 5. Okay. And because I'm running out of space here, I'm not going to be able to fit all of this onto this board, but I'm just going to calculate this number, subtract the 2, and it will give me theta. Okay. So theta is going to be, well, maybe I will be able to fit it. Let's see. Inverse tangent of 7/3 minus the inverse tangent of 8/5, and that's going to be approximately equal to 8.81 degrees. Now I can take this number and substitute it in here, and that will help me see that 250 cosine of 8.81 is equal to E. And so whatever that number is, I'm going to take it and multiply it by the square root of 89. So now I know that W is equal to 250 cosine 8.81 times the square root of 89. And that means the amount of work that's done in this case is 0.69 foot pounds. And there you have it. So this is a very complicated problem, and if you had a hard time with this, that's okay. Just go over it again. Ask your teacher for help to maybe see this problem from a different angle. But the one thing I want to stress here is that this entire problem, once we get all the vectors figured out, it reduces to finding this angle here between two vectors. Because you have a vector, the green vector here, that's pointing in some direction. You have another vector, the red one, that's pointing in some other direction. And we're interested in the angle that's in between the two of them. And we really needed to use some of the examples from the previous problems in order to get that done. Thank you for watching, and have a wonderful day. Good morning, Louisa. Yes, you can.